How's it going, everybody? And welcome back to our Cisco Enterprise series focusing on CCNA, CCNP, and CCIE. Before I get into any of the network fundamentals about, routers, switches, firewalls, all that good stuff, I want to start back even further than that at the fundamentals. I'm going to actually jump ahead a little bit to compare TCP and UDP. And what I've done is a quick Google search. Rather than going through the minutia of creating a bunch of slides and whatnot, I'm more of the, let me just Google something and give you something very easily searchable for yourself. Because that's one thing that you're going to have to become good at, regardless of your level of skill or how long you want to be in the industry or whatever the case might be, is your ability to research information relevant to the topic at hand. So in this case here, I wanted to talk about the OSI model and the TCP IP stack and how that works and what the difference between the two are and why you would care. So let me jump over here. Here we go. This is the one that I wanted to go over with. So let me go ahead and get out of the way. And we're going to talk a little bit about this. Let me blow this up a little bit so you guys can see this a little bit better. So we're going to start from the bottom and we're going to work our way up. So there are, this one here. Okay, so there are two different models that networking folks and some application folks are going to leverage. And the first one is going to be the OSI model. The OSI model stands for the Open Systems Interconnect model. And essentially all that means for you and I is, how do I go about addressing the different layers of the application flow, from the application layer down to the physical layer, and from the physical layer back up to the application layer. And a great example of that is this, where you have a transmitting device and a receiving device, or a sender and a receiver. Now, the way that, so this, I find it funny that they misspelled that. Anyway, there is going to be a lot of information inside of the stack, and one of the common terms that we're going to have to be familiar with is the concept known as encapsulation. Encapsulation is, in the easiest definition I can give you, is the adding of information, and the decapsulation is the removal of information. So that information could be a TCP/IP info, that information could be an IP address, it could be a MAC address, so on and so forth. So as you are going through your top-down or bottom-up view of how networking traffic flows, these are going to be some information bits that you're going to want to be aware of. So before we get into how the transfer of information works, let's talk about what it looks like. Why do we care? So when we talk about the physical layer, this is going to be anything you can put your hands on, right? For the sake of argument, you can still touch a wireless access point. You can still touch the wireless antenna on some old school laptops and things like that. So when we talk about the physical, we're talking about 802.11. We're talking about 802.1. We're talking about 802.3, so on and so forth. So there's going to be things that you can touch, right? The router, the switch, the firewall, the access point, the laptop, the server, stuff like that. Those are going to be, that's the physical layer. Anything above that, layers 2 through 7, that is going to be more logical. And so what do I mean by logical? Well, you can't touch the logical, right? It's all inside in the brain, I guess you could say, or inside of the physical. So, for example, whenever I cook steak, right, or a hamburger or whatever it is, there is a process to go through that, right? So the physical, you got the piece of meat in front of you, and you take that piece of meat and you cook it to a certain doneness. So inside of that, you can either cut it open to see how done the meat is, right? So if somebody orders a steak and they say, I want it to be medium, they want it to be a certain amount of doneness, but they want to have a little bit of pink in the middle. So, okay, fine, that's their preferred doneness. Now, there's two ways to achieve that. You could either, or technically three, for the basic cook like myself. We could either cut the steak open and look and go, okay, well that's a pink, so it'll work. That's a medium doneness. Or you could stick a pen thermometer into the meat about halfway through or so, and rely on the tip of the thermometer to give you a temperature reading. If you know what the temperature correlates to the doneness of medium, then you'd be like, okay, 135, it's medium. Perfect, the steak is done. Or if you're like an advanced chef like, Gordon Ramsay or, any of those guys that are out there, you can touch it, and based off of the doneness, I know there's like you have the finger test where it's pinky, ring finger, middle, index, and you push on the soft tissue here in between your finger and your thumb, and as you get further up, it's supposed to get squishier or more difficult to push in. At least that's the rule of thumb that I've heard. So I've always been either let me cut it open to look, or let me stick a thermometer in to get a temperature reading. That's the logical. You don't know, you can't tell what it is by looking at it unless you have timed it and okay, at this particular temperature, on this particular part of the grill, that the steak is going to be this done after this amount of time. Some people have that level of understanding. I do not. I don't really know where the hot spots on my grill are. I'm not that into it. I will rely on a tool, thermometer, or cutting open the piece of meat to look at the doneness to go about it that way. So think of that. The outside structure of the piece of meat is the physical, right? You can physically touch it. Beyond that, you don't know how done it is unless you're, I guess you could do a visual where you could see the red coming out and the blood and whatnot, and it's going through that process. So one way or the other, that's essentially what you need to be cognizant about when it comes to the logical. It's all the stuff happening inside of the equipment. So there's going to be some interaction there, whether it's you're using RS-232 or a console cable. That's that baby blue console cable that everybody is very, very familiar with. I don't have one handy, but if you were to Google Cisco baby blue console cable, it's going to show up with a DB9, meaning there's going to be a 9 port connector, I'm trying to think of the word to use, but it's going to have 9 holes in it, so it's going to be a female adapter, so you're going to plug that into a male connection. So that's the old school way. Nowadays they're coming out with USB ones where you literally plug in USB into your laptop and you plug the other end into the console port of your device. So a lot of equipment nowadays comes with the USB version of it. It's just way easier to use. So that's the physical. So that's how you would interact with the physical if you don't already have a logical way of connecting to it. What would be a logical way of connecting to a network device nowadays? Well, that would be SSH, secure shell. So it allows you an encrypted connection between you and the device. And actually, I'll give you a great example of what that might look like. Let me go ahead and go to switch 1. I just SSH'd into my home switch. That's it. Show IP SSH. Show IP SSH. Show users. So here I am. I'm connected in VTY0 virtual teletype. Rob is my username, and that's the IP address I'm coming from. So I just SSH'd into my home network, into my home switch. So I'll go ahead and exit out of that just to give you an example of what that would look like. That's an application. I'm using PuTTY, or in this case here, Secure CRT, to log into the device. So that would be an application and using the entire stack to get to where I'm going to go. Now, the physical addressing, you have Ethernet, right? The Ethernet, you've got the MAC address, you've got the LLC, 802.11. 802.11 is the wireless standard. So as I was saying, 802.11 is the wireless standard. So you have 802.11 AC for one of the newest wireless standards. We're not really going to get into a whole lot of 802.11 because it's wireless stuff, but if you want to dive into that, there's a whole bunch of documentation online for that. Yeah, layer 2 framing, you've got the MAC address and the logical link controller. The MAC address is going to be what everybody's familiar with. And if you don't know what that looks like, let me go ahead and pull this up real quick. And this is my home computer. I'm going to do a ipconfig /all. So if we look right here, this is my MAC address. I have a wireless adapter, and then I have Bluetooth on this as well. Then I have my my wired connection. Here's my MAC address. This is my physical address on the network. So this is the MAC address. If you were to take the MAC address and think of a 2-layer cake, the bottom layer is going to be your MAC address. The top layer is going to be your logical link controller. The logical link controller is going to be, or control I should say, not a controller. The logical link control is going to be the information that is signaled between the layer 2 and layer 3 header, which is going to be your network layer. And essentially what that means is it's signaling from layer 2 to layer 3, okay, this is an IP packet, and based off of some information in the layer 2 header, what is known as the ether type value. We'll talk a little bit more about that when we get into the weeds. We start doing some Wireshark lookups and things like that. But the ether type value, for example, 0 by 800 would be an IP packet. If you're dealing with MPLS, that's going to be a different packet. If you're dealing with VXLAN, that's going to be a different type of packet. So these are all things that are going to come into control. So the MAC address is what most people are going to be familiar with, because we care about layer 2 information, because you do a show MAC address table to show what physically connected devices are being learned, stuff like that. Where LLC is the second half of that. That's going to be, okay, we know it's we know it's Ethernet media as the connection type, and then on top of that, we know that it's an IP packet coming, which is going to help signal to the network layer, okay, it's an IP packet, and all that good stuff that goes along with that. And then you'll be able to dive into ARP, Address Resolution Protocol. We're going to talk a little bit about that in the future. Actually, all of these topics we're going to be talking about as we go further up the road. We have IPsec for doing data encryption. If you wanted to do VPNs, whether they're site-to-site or remote access, you can do IPsec VPNs with that. ICMP, a ping packet, the Internet Control Messaging Protocol. It's going to be how devices on the network are able to talk to each other without actually sending any real data. IGMP, this is how a user, an end user, would signal to the network, I want to receive multicast traffic. So Internet Group Messaging Protocol. Then you have OSPF. Technically, this is wrong. So you might say, well, how is that wrong? I'll get into that, but technically speaking, the OSPF, EIGRP, and ISIS and RIP do not operate at layer 3. They operate at layer 4. And BGP, well, technically they all operate at layer 4 because they happen to use UDP. BGP is the only one that uses TCP. All the other ones use UDP communications out of the gate. And we'll talk a little bit about reliable UDP. There is such a thing as reliable. It's unicast, but it's still UDP communication. So we'll talk about how that comes into play down the road. But this is technically not accurate. OSPF, they rely on an IP address and they do discovery, but the way that they do discovery is actually happening at layer 4. And we'll talk about how that actually happens behind the scenes. Rewind that. EIGRP and EIGRP and OSPF are technically IP protocols because they have their own, what's the word I'm looking for? They have their own, there's a term for it, I can't remember off the top of my head what it is. IP protocol number, IP protocol 88 and 89. So I need to correct myself. So EIGRP and OSPF are so well known they have their own, what is this here? We're going to say OSP protocol, all protocol number 89, and then EIGRP protocol number is 88, right? So EIGRP is 88, OSPF is 89. So this technically, in this case here, is actually accurate. I'll stand corrected. As I was thinking about that, they do have their own IP protocols. ISIS does not. Technically, ISIS is ISO 10589, I think is what it is. And so RIP or BGP uses layer 4 because it's a TCP. It's an application. We'll get into how that works later on down the road, but we'll see what that looks like. But BGP uses TCP port 179 for communication, and we'll talk more about that, what that looks like. And then you've got the transport layer. The transport layer is going to be, once you have end-to-end connectivity in place through IP connectivity, then you can start relying on the transport. What is that going to look like? So this is going to be more than one hop away. It can be one hop away, depending on the situation. UDP traffic, when it comes to like routing protocols, it uses link local multicast for all the IGPs, OSPF, EIGRP, and RIP to discover other routing protocol speakers on that same segment. And we'll talk about that. We'll see what that looks like further on down the road. But then you have BGP uses its own, where it uses TCP port 179. That's a well-known port number for BGP. Then you got things like secure copy, SSL, secure sockets layer, and then TLS, transport layer security. So this is going to be more or less going to be the protocol you're going to use for remote access VPNs, if you're doing a web-based VPN, stuff like that. So these four here are considered the network layer in the TCP IP stack, which is this guy. So transport layer, so I could still consider a network, but if you look at the TCP IP model, the physical layer and the data link layer are considered network access layer. Ethernet token ring, which nobody uses, ATM and frame relay, these are both legacy. The only one that's really modern still today is going to be Ethernet. Then you get to the network layer, and there's the internet layer, also referred to as IP. So you've got ARP, IGMP, ICMP, all that good stuff that goes along with that. The transport layer is TCP and UDP, even though from an OSI perspective, there's more to it than that. Then session, presentation, and application are all part of the application layer. So you have HTTP, so web, email, telnet, file transfer, looking up named IP resolution, RIP, which I think is funny because I don't agree with that at all. RIP is actually not, doesn't have anything to do with this. And SNMP for doing network monitoring. So simple network monitoring protocol. So there's that. So if we come up a little bit higher, maybe they meant to say RTP. That would make sense. Or FTP. Maybe that's what they meant there. I really don't know. Session establishment. So these three right here, session layer, presentation layer, and application layer, we really don't care about. We can't go in and from a networking perspective, we care about 1, 2, 3, and sometimes 4. So let me give you a great example of how that would work. Let's say, for example, a user calls in and says, hey, this isn't working. Like, okay, cool. Like this web page or web server isn't responding. I'm getting a 404 or whatever the error code is for a web server is down. Okay, great. What you can do is you can literally open up a telnet connection from your computer, as long as it's going to work, and you can telnet to that port of 80. And so you have the IP address of the server. So let's say it's 10.1.1.62, right? So you telnet to 10.1.1.62, and you put in their port 80 as a telnet port. So what I would do is this. Pull up this again, and then from here, I would type in telnet. I don't think it's going to work. 10.1.1.62, port 80, right? And telnet is not recognized. Okay, perfect. That's exactly what I expected. So let me go back over here to, let me pull up PuTTY. Where's PuTTY? PuTTY's right here. So I'm going to pull this up here. We're going to go to other telnet. We're going to type in 10.1. I think it's 255.1.60. And we're going to put in here 80. Now, this pops up right here. I have an active connection. It doesn't say inactive. Now, if I was to do this, let me go ahead and plug in 10.255.1. I don't know if it's gonna work. Actually, I just heard it fail. Okay, so let me go to 62. Let me try 63. 10.255.1.63. There. Okay, so this happens to be a virtual Fortinet firewall that I'm testing some stuff out on. If I was to go in here and say, okay, close that out. Let's try that one more time. So in this case here, we're going to go to not secure. So we're going to type in 10.255.1.63, and we're going to put in here, let's go to other telnet, we're going to put in here 80. So it's attempting to connect. So it closed out on me. So I can go back over here to this guy. We're going to do 10.255.1. And it's secure. It's not secure, right? So 443 would be the port number, right? So secure connections, 63. We're going to do other. We're going to come over here. We're going to say 443, and we're going to click on open. Bring this guy over, and it closed out. So the connection's open, right? So you could, if you've got a scenario where you're trying to test connectivity, but the web server's not working, you can do a telnet connection to it and then have the web admin, this is kind of you normally wouldn't do this, you just call to verify the network is not the problem. You would then go through and then have the server admin or whatever open up, what is it? It's netstat-nao. Right, and so it's going to show you all the different connections that are out there. Right, so I've got a bunch of web pages opened up, and what you do is you would look for an open connection, an established connection like this, and what that would do is show you the connectivity. Right, it's like, okay, well, there's an active open connection to the server, which means the IP address is working, the socket on the stack and the TCP IP stack, that's working. However, the service for HTTP may not be. Therefore, the admin would have to go in and take a look at what's going on and then go from there. That's where that comes into play. So 5, 6, and 7, you and I really don't care about. That's beyond our capability of troubleshooting, diving into. All we can basically do is verify from layers 1, 2, 3, and 4 that we can get there. And sometimes 4 is hit or miss. If I can ping it, fine, the IP address is responding. But you got to remember, the IP address is here. You have applications and services that are running on the server that may not be responding. So you might have the web server is running on top of that, but let's say the web service, for whatever reason, is just overwhelmed. There's a memory leak on the server, or whatever the case might be. You run into these problems that the only way to troubleshoot them is to have the person that owns that server to take a look at it and figure out what's going on. So it might be a reboot, might be a bunch of other things. But that, at the end of the day, is essentially what that looks like. And you can see here we have email, we have web. This guy is pulling up a Google, he's on a Mac, and he's pulling up google.com. So that's where the network processed application. So 5, 6, and 7, you and I don't care about. Nothing, not a whole lot you and I can deal with when it comes to that. So we just chalk it up to, okay, well, we've done all of our due diligence up to this point. We have to hand it off to the application team or the server team. Now, from this one here, this might be RTP, real-time transport, which is going to be what voice over IP traffic uses. So the TCP IP, there's 2 competing models at the time. So what's actually kind of funny is OSI was a better standard, right? A better model. It's more in depth. It's got more individual pieces to troubleshoot. For whatever reason, and I don't know the background behind this, but for whatever reason, the OSI model is what networking folks learn so that they understand the entire stack. What I find is funny is the TCP IP model won. So if you look at OSI OSI is basically IS to IS. And so when we take a look at how that actually works, it's interesting that the OSI model is how networking folks like you and me learn how the network layer works and how networking operates in the different layers. So we have, the physical, we have switches, we have routers and firewalls and access points and stuff like that. So so we have layers 1, going back over here. You and I are going to pay attention to 4 different layers. We're going to pay attention to layer 1, layer 2, layer 3, and layer 4. So if I happen to say a layer 2 switch, layer 2 means MAC address. If I say this is a layer 3 interface, it means I'm talking about an IP address. So, and I will reiterate this over and over and over again. If you're just brand new into networking and into how all this type of stuff works, and you're trying to correlate layer 2 versus layer 3, that's the simplest way to correlate it. It's going to be layer 2 is a MAC address, layer 3 is an IP. So they're both technically logical information for you from what happens inside the box, but do understand that the MAC address is considered the physical address and the IP address is considered the logical. MAC address, when they say physical, means it doesn't change. You can change a MAC address. I'll be honest with you. You can do that. But out of the gate, there is going to be a MAC address auto-assigned by the operating system on that individual device. It's already burned in. So what's going to happen, the BIA, the burned in address, the MAC address is going to be automatically assigned. It's assigned when the card, the actual network interface card, the NIC, is manufactured. That MAC address is burned in at the time of manufacturing. So you will find as time goes on that the MAC address is the burned in address, the IP address is the logical. The IP address can change on a device. So when we talk about dynamic addressing like DHCP, you talk about a large call center where you've got all these devices are connected to the network, but they get their IP addressing, their DNS information all through DHCP. In that particular case, the IP address one day could be, or they usually have a week lease time. So, for example, if PC1 in your call center gets the IP address of 10.1.1.11, on the second week on Monday, it might get 10.1.1.12 because another device in the network might have already gotten 11, depending on the situation. It's problematic to try to figure out what device is going to get which IP address unless you put in reservations and you say this MAC address will always get this IP. Depends. That could be the case, and there is a way to do that. But one way or the other, the MAC address is a burned-in address. It's always going to be the same. Where a IP address is going to be can move. So, for example, the way I analogize this, and the analogy that I like to use is this. I have a home. I've lived in the same home for many, many, many years. Well, the home address doesn't change, right? My address does not change. We'll say 123 Main Street in anywhere USA hasn't changed in the last 20-ish years that I've lived in this house. Well, what's interesting about that is 20 years ago, I didn't own this house. So somebody else lived here, but the address hasn't changed. The people that live in the house or live in the home and come and go every day, they're the logical piece, where the home address is the physical burned-in address. It's never going to change unless the house is torn down and the street that I live on is ripped out. There's a plat map for the city, and they know that 123 Main Street in any city in any count in any city any state USA, it's always going to be the same. That's the burned-in address. It's never going to move. But the people that live in that home can rotate every so often. So for the last almost 20 years, I've lived in this house. So my wife and 2 boys, we were the logical component to that. So, and then depending on anybody else that decides to come over based off of, birthday parties, family, that type of stuff, those are the things to keep in the back of your head. So I hope that makes sense to everybody watching, because that's essentially how this operates. So if you understand that and how the home's address is always going to be there, and now I'm going to go off on a tangent here for a second. That doesn't apply to like RVs or mobile homes or a camper that you eventually make a trailer home and you decide one day you're going to move from Arkansas to Florida, or you're going to move from Florida to Texas, or whatever the case might be, and then that physical that home gets up and moves somewhere, right? Well, in that particular case, it's no longer that physical address. It's got a new address. Okay, fine. But what's interesting about it is whether or not there's actually a dwelling on that property is technically irrelevant. That property sits on a street, whether it's a name or a number, and it's got a number attached to it. The plat map figures that out. So think of the plat map, PLAT, the plat map, as your network switch, and you've got 48 ports on it, right? So we're going to talk in ports of 48 port density. So that's how I want you to think about that. So I'm going to try to remember this analogy as we talk through the rest of the series and go through those details, but that's essentially what you guys need to worry about. Now that we've talked about that and we understand layers 1 through 4, let's talk a little bit about how the encapsulation process works. So I'm going to come back over to here. So encapsulation is this side, top down, and then you have decapsulation, which is from the bottom up. So from the top, I don't really care what the application is. We have, let's say it's a TCP connection, so you've got user talking to a web server. They go to google.com. They don't do anything on Google. They just pull up the web page. There's still a transaction of data between the server and the user in order for that to happen. What ends up happening is the server is going to send data back. So we have a request that goes out, and then we have a response that comes back. We'll talk more about how the TCP SYN-ACK process works later on. The SYN, the acknowledgement, the SYN-ACK, all that good stuff, the three-way handshake. We'll talk more about that in detail later. But the server is going to take its payload and its web page. Essentially, this right here is going to be delivered via this. So we're going to have our application, presentation, and what is it again? I forgot. Session. So we're going to have our application, presentation, and session information. This is all data traffic. Then the TCP communication, sequence and datagram stuff. That's all going to be encapsulated to a TCP header. So you got the data, the TCP header is going to be attached to it. So we have a source and a destination. So we have a source port, destination port that goes into that. Then we're going to have a TCP, we're going to add an IP address, source IP, destination IP. Then we're going to have MAC address. Now, when this down to the IP TCP stuff, this is all logical, right? Down here, we're talking about on a hop-by-hop basis, the MAC address will change. We'll talk about that more in detail later. But as we go through layer 3 interfaces, the MAC address will change. Because remember, the MAC address is physical. It never changes, right? So as you pass through what I refer to as intermediary devices, network equipment, network devices, routers, switches, firewalls, that type of stuff, access points, the MAC address will change on a per hop basis. And we'll talk about more on that later. But for right now, this is layer 2 and this is layer 1. Layer 1 is going to be in binary. It's machine code, right? How do computers talk to each other? Through binary. And they're able to take all that binary information with all this encapsulation, they're able to send it over the wire. So that's why when we talk about things like MTU, the maximum transmission unit, and things like that, you'll send traffic over the wire or over the air if you're talking about wireless or 4G LTE, things like that, microwave communication, stuff like that. You'll get over here, it'll be received as bits, but then as it gets up here to layer 2, you'll talk about frames and the MAC address and the TCP, the IP, the data, the frame check sequence, making sure that the frame hasn't been corrupted in flight and things like that. Then you start to decapsulate. You'll start to rip off the layer 2 header. Then you'll rip off the layer 3 header. Then you'll rip off the layer 4 header. And then you'll start delivering the data back to the user. And we'll talk more about that because We'll talk about it, especially when we get into like layer 2 flooding and how that works, and then we'll talk about how a router routes and how it makes a decision-making process. This all this information will start to become more and more evident as we get further into the details, but that's essentially what it looks like. So then once we have all of that in place, we'll have end-to-end traffic flows. This is really important to understand because we have encapsulation on the left and we have decapsulation on the right. So, and can it flip-flop? 100%, it always does. So you're gonna, if the user sends a request to the server for something, let's say for example we go from this and we click on a little blue button in the right-hand corner, which I believe will be like you want to log into Gmail. It's probably an older picture, but one way or the other, you click on that. If I click on here, the images are Gmail, to go into my Gmail account, I'm sending a request to the server, right? So what ends up happening is I reverse the process. Instead of decapsulating, I'm encapsulating. I send all of my traffic back down. I go data, 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 then I throw a TCP header on it, an IP header, on my MAC header. I have all this encapsulation, and I send it on the wire and send it out to the server to get a response. The server is then going to get it and reverse the process. It's going to rip up the layer 2 header, rip off the layer 3 header, rip off the layer 4 header, and eventually expose the data, and then voila, my Gmail account will pop up. And then I'll be able to click on literally any click you do on a web page is going to be a request from you to the web server or email server, whatever it is. And then the stuff's pretty quick, right? We're talking milliseconds of response time, even if it's hundreds of miles away. You're going to get a response. So if I click on an email, then I'm clicking on that link, which is telling the email server, open that email. And then there's that encapsulation process to decapsulation process, right? And then so on and so forth, it goes down the road. So this will continue to happen hundreds of times a minute, probably thousands of times a minute, depending on what you're clicking on or stuff like that. If you're scrolling on your phone, if you pull up, I don't care whether it's Instagram, TikTok, YouTube Shorts, or you're watching a YouTube video, or a Facebook, or scrolling, whatever, you're on a dating app, I don't care what it is. As you are scrolling through your phone, right? I've got my phone here. Like I'll start scrolling through my phone, and as it goes in, it's sending more and more requests to the server. I want you to send this video to me. Send this video to me. Send this video to me. Click on the comments. It loads the comments. That's a request out to a server and a response back from the server with the information. So this is all information that you need to be aware of and how it happens. And every time you scroll up, that the encapsulation and decapsulation process happens thousands of times per minute. That's why high-speed networks are kind of a requirement today, because they're necessary. So I'm glad I was able to go into this because I'm hoping that paints a good solid picture for you in terms of how the day-to-day operations work and all that stuff that goes into play. Because once we get beyond layer 4, TCP or UDP depending on the scenario, and I'm not going to get into the difference between TCP and UDP right now because that's going to be a whole separate video. I'm going to go into the details on that. But that's essentially what it is that we're attempting to do. We're attempting to move data through the network as quickly as we can and as efficiently as we can with the least amount of errors. That is the goal. So I hope that it was informative for you and answers the questions that you might have had on how all that type of stuff works. With that being said, ladies and gentlemen, I want to thank you guys for stopping by and hanging out with me in this video. If you have any comments, questions, concerns, or anything like that, please drop that in the comment section below. And if you haven't already done so, please like, share, and subscribe. And I'll catch all of you fine people in the next video.